Hello, my darling dears, my precious little chickadees. Welcome back to our flipped classroom. Third time's the charm. And today, perhaps fittingly in my absence, we are introducing our last new content of the year. Pause for sadness. Pause for overwhelming despair. Pause for so many tears. And we're back. Let's talk today, class 6 of unit 8, about the law of cosines. So last time we were together, we extended the area formula for a triangle using some trigonometry so that we no longer need a right angle in order to find our area. Then we used that area formula to develop what we called the law of sines. Take a look back in your notes. Remind me, what are these two formulas that we generated together? Go. And stop. Well, first of all, we know that now we can find the area of any triangle, regardless of whether it's right or not, using our trig function of sine. So we can say that the area of a triangle we now know is equal to 1/2 side length A times side length B times the sine of that angle C that is included in between sides A and B. And using that sine formula, there are 3 ways to find the area of any triangle. If we set all 3 of them equal to each other and simplify as much as possible, we get what we called the law of sines, which says that the ratio of the sine of any angle to its opposite side's length is the same regardless of which angle and which side in the triangle we choose. Fantastic. Now there's one more law that we want to identify together, and it's called the law of cosines. The motivation behind it is very similar here. By extending the area formula for a triangle to any triangle, we came up with these 2 formulas. There's another formula that works very often with right triangles that we want to extend to any triangle, and that formula is our iconic Pythagorean theorem. We want to know if there's a similar extension for the Pythagorean theorem that can let us find side lengths regardless of whether our triangle is a right triangle or not. Let's derive this together. So similarly to what we did with our area formula, let's begin. If we need the Pythagorean theorem to start, we need to find a right triangle somewhere. So I'm going to draw an altitude. It doesn't matter which one we draw here, but I'll use this guy just because most often it's easy to visualize when we're drawing our altitude from the top of the triangle to a base, right, that's horizontal. So from here, I'm going to call this altitude H. I'll call this side here on the right that we split that side little b into X. And then I hope you can agree that this length over here, well, if the whole thing is b and the part over to the right is x, this guy is going to have a length of b minus x. Now, the thing about this is that we don't know what h and x are. We've created them arbitrarily, but we do know the lengths of a, b, and c, we're assuming. So if I can find a way to write h and x in terms of a, b's, and c's, then I should be okay. Well, here, looking at that triangle on the right, which I'll shade in here in pink. This triangle, if I want to turn h and x into stuff with quantities that I already know, well, I can use a little bit of trig to do so. Let's start with x. Now, x I don't know, but I'm assuming that I know the length of a, and I know the measure of angle c, which tells me that I can use sine. So, or not sine, sorry, but cosine, because here x is my adjacent, a is my hypotenuse. The cosine of angle C should be equal to x over a. Now, if we multiply both sides by a, we can accomplish that goal of re-representing x in terms of known quantities. Here, x is going to be equal to a times the cosine of c. We can do the same thing with h, right? h, a, and c. These guys are connected by our sine function. So we can say that sine of angle C would be equal to our opposite side h over our hypotenuse a. Same goal, I want to get h in terms of stuff I already know. Well, let's multiply both sides by a. Here, h is equal to a times sine of c. Now, we've used this pink triangle. Let me now, in green, highlight this triangle over on the left. Now for this triangle, my goal is to use the Pythagorean theorem. Let's set up a Pythagorean relationship. Well, I know that the sum of the squares of the lengths of my legs, which in this case would be h squared and b minus x squared, that should be equal to the square of the hypotenuse, which we've got as c. Now same move. Again, I want everything in terms of a's and b's and c's. Well, I already know what this x and this h are. Let me use that to my advantage. So doing some substitution here, h squared I can rewrite as a sine c squared from what we found above. And then here in my quantity, I can write this as b minus x, which we've identified is the same as a times our cosine of c squared, which is equal to that length lowercase c squared. All I need to do now is simplify. Well, let's take a sine c squared. A simpler way to write that, if I do a sine c times a sine c, I can do a times a, which is a squared, and sine times sine I know is sine squared. So this is a squared times sine squared c. And now I have b minus a cosine c quantity squared. You may notice that this is not a Pythagorean, but a perfect square trinomial. Let me write this out and do our met-wet here just to make it more obvious what's going to happen. So I know if I square something, I'm really just multiplying it by itself. So let me write out that this is b minus a cosine c times itself. Now doing my met-wet, I'm going to start by taking my b times b, which is b squared. Let's do b times negative a cosine c, which would be minus ab cosine c. Same thing from that guy in the middle. This is going to be another negative ab cosine c. And then at the back, I have negative a times negative a, which is positive a squared, and cosine c times cosine c, which is cosine squared of that big C. All of this is equal to c squared, right, when I add that a squared sine squared c from above. Now let's combine some like terms. First of all, I'm just going to rearrange so that these guys are next to each other. We're going to see why momentarily, but let me take a squared times sine squared of c. I'll put a squared times cosine squared of c right next to it. I've got plus b squared there. And then I also have some like terms. I have a negative ab cosine c and another negative ab cosine c. Putting that together gives me negative 2ab cosine c's. All of this equal, of course, to c squared. Now the last thing that I can do, notice that both of these terms have a common factor of a squared. Just for funsies, I'm going to factor it out to see what happens. So both of these have an a squared. That leaves me with a sine squared c from the first term and a cosine squared c from the second term. Now the thing is, even though we might not realize it, there's something really interesting about this stuff in here. Think back to Unit 7. We worked with some identities when we were doing trig. Can you tell me what sine squared c plus cosine squared c would need to be equal to? 10 seconds go. And stop. Well, you may remember we used the Pythagorean theorem to find some Pythagorean identities. And the most obvious one, or at least the one that we kept coming back to, if I take sine squared of any angle and I add it to cosine squared of the same angle, will I always get 1? Which means that sine squared c plus cosine squared c, that's equal to 1. And a squared times 1 is just a squared. I've got that plus b squared over here, minus 2ab cosine c, all equal to c squared. This is what we call our law of cosines. Now, just to write it out here formally, this is our law of cosines. And the law of cosines says that a squared plus b squared minus 2ab cosine c is equal to c squared. And the important thing to notice here, a, b, and c are just any sides of a triangle. It does not matter. But the important thing to remember is that this angle c is going to live where relative to which sides, right? This big angle c, where does it need to live relative to the other sides in my triangle here? 5 seconds go. 4 seconds go. 3 seconds go. 2 seconds go. 1 second go. Half a second go. Okay, enough. From here, big angle C, this is just the angle in between those sides A and B. Right? More formally, we can say that this is the angle that is included between sides A and B, right? But as long as I know two side lengths, A and B, and the angle in between them, then I can find the length of that third side, C. Very nice. Now that we've got it, let's do a little bit of practice using it. So I want to find the length of x using my new law of cosines in each of these triangles. Give yourself a little bit of time. Let's see how far we get. Try it out. Okay, so here for part A, I have two sides 4 and 5 with the angle 111 degrees included in between them. This is prime law of cosines territory. Let me, just to be safe, write that law of cosines once again up here. I know that a squared plus b squared minus our 2ab cosine c is going to be equal to c squared. From here, right, all I need to do now is plug in. So I know that A and B are my two sides. Big angle C is the angle in between them. So using my formula, I can say that 4 squared plus 5 squared minus 2 times 4 times 5 times the cosine of 111 degrees should be equal to that guy x squared. All I need to do now is simplify. Well, 4 squared is going to be equal to 16, plus 5 squared, which is 25, minus 2 times 4, which is 8. 8 times 5 is 40, times our cosine of 111 degrees is equal to x squared. Let me combine my like terms. Well, 16 plus 25, that's equal to 41. So 41 minus 40 times the cosine of 111 degrees is equal to x squared. Now I want to get x by itself. In order to do that, let me take the square root of both sides, which tells me that x is going to be equal to the square root of 41 minus 40 times the cosine of 111 degrees. Now you're totally welcome to leave it like this in your calculator ready form. If you were to plug this into a calculator, right, you would technically get plus or minus here from taking the square root of both sides, but again, length can't be negative, so we will assume this is the principal root, just our positive case. This number is approximately 7.44, which if we take a look back at our triangle, we should hopefully see, or agree at least, that this is a relatively reasonable answer for x. Very nice. Let's try the same thing here with b. I've got 5 and 7 as my side lengths, with the angle 60 degrees included between them. Once again, I can slot everything right back in to my formula. So here, using my law of cosines, I know that 5 squared plus 7 squared minus 2 times 5 times 7 times the cosine of 60 degrees should be equal to that side x length squared. From here, let me simplify. Well, 5 squared I know is 25. 7 squared I know is 49. And then I've got negative 2 times 5, which is negative 10, times 7, which is negative 70, times the cosine of 60 degrees. Well, cosine of 60 degrees, we'll remember from our best friend chart, is just 1/2. So I've got 25 plus 49 minus half of 70, which is 35, all equal to x squared. Well, 25 minus 35, let me do that first. That's negative 10. 49 minus 10 is 39. So 39, putting these all together, is equal to x squared. Once again, to get x by itself, let me take the square root of both sides. Here, x is going to be equal to, technically plus or minus, but again, length can't be negative, so we'll just assume we want the positive case, our principal root, and the square root of 39 is approximately 6.24. Very nice. One last one here for the road, a little bit more complicated for reasons that we'll soon see. We can also use the law of cosines when the side length that we're solving for is not opposite the angle that we're given. The only thing here is that it might just be a little bit more interesting how we find that value of x. Let's use our law of cosines here. Give yourself a couple minutes, try it out, see if you can find a value for x, and tell me what happens. There's going to be something a little wonky that we need to account for. Go ahead. And stop. Well, we know our law of cosines. For the sake of it, let's write it down one more time. We know that a squared plus b squared minus 2ab cosine of uppercase c is equal to lowercase c squared, where a and b are our two sides and big C is the angle in between them. Well, here, as I slot things into place, it's just going to take a little bit different of a shape. Well, a and b, these are going to be our 10 and our x. So let's say x squared will have as our a squared, 10 squared, which is going to be 100, will become our b squared. And then here I have negative 2 times a, which is x, times b, which is 10, times the cosine of 45 degrees for c, and then c, our opposite 45-degree side, that's 8 here squared. Let's simplify and see what happens when we solve for x. Well, I've got x squared, which I can't do anything with. 10 squared is 100. And then negative 2 times 10 I can write as 20 times x at the back. And cosine of 45 degrees, we'll once again remember from our best friend chart, this is the square root of 2 over 2, all equal to 8 squared, which is 64. From here, once again, I want to simplify as much as possible. So I've got x squared plus 100 minus 20 times the square root of 2 over 2. Well, I can cancel out the 2 in the numerator and the denominator. 20 divided by 2 is 10. So I've got 10 times x times the square root of 2, which I'll write like so, is all equal to 64. Well, this is a quadratic equation. The best way that I know to solve a quadratic equation is to get a 0 on one side. So let me minus 64 from both sides. I'm going to write this now as x squared minus, for the sake of getting it in standard form, let me put the x term second, and then at the back, 100 minus 64 is 36, all equal to 0. Now, I don't know how to factor this. Let's try the quadratic formula. So the quadratic formula, let me identify my a, b, and c here. My leading coefficient a is 1. My middle coefficient b is negative 10 root 2. And c here is 36. Now slotting into place, I know that x is going to be equal to negative b, which would become positive 10 root 2, plus or minus the square root of b squared, so this would be negative 10 root 2 squared, minus 4 times a, which here is 1, times c, which is 36, all over 2a, which would be 2, times 1. Simplifying as much as we can. Well, we've got 10 root 2. Can't do anything with this guy yet. Plus or minus the square root of, well, negative 10 times negative 10 is 100. The square root of 2 times the square root of 2 is 2. Multiply those together. negative 10 root 2 squared should be 200. 4 times 1 is 4. 4 times 36 is 144. So inside of my square root, I'm now taking the square root of 200 minus 144, all over 2 times 1, which is 2. Now I've got 10 root 2 plus or minus the square root of 200 minus 144, which is 56, all over 2. Once again, I want to simplify here. So this is going to become 10 root 2 plus or minus the square root of 56. Well, the square root of 56, you'll hopefully notice the greatest perfect square in the factors of 56 is 4. 4 times 14 is the square root of 56, so I can simplify this as 2 root 14 all over 2. And then my last move here would just be to divide both of these by 2. Well, 10 divided by 2 is 5. 2 divided by 2 is 1. So my final answer here would be 5 root 2 plus or minus the square root of 14. Well, the interesting thing about this is that if I were to split this up, I have 2 different answers. Either x is equal to 5 root 2 plus the square root of 14, or x is equal to 5 root 2 minus the square root of 14. And even weirder, if I were to plug both of these into a calculator, it turns out that usually we end up with one of them being negative. Here, both of them are positive. The first one works out to something like 10.81 approximately, and the second one works out to something approximately around 3.33. Now, in context, both of these are possible answers. Neither of them are negative. I can't rule either of them out. So the only thing I need to figure out is, well, in context, why would it make sense that I have 2 answers? And there's a kind of wonky answer to this question that ties back to some interesting theorems or maybe non-theorems that you discussed in geometry. Why do you think it's possible that I can have 2 correct answers here for the value of x? Go. And stop. Well, the important thing to remember here, there are 2 possible answers because with the configuration of angles and sides that I gave you, there are 2 possible triangles that we could create. The first one here would be the original one that we started with. I don't remember exactly what it looked like, but it was something like this. I had an 8 over here, a 10 over here, an x over here, and then my angle measure was 45 degrees. So it's possible that that side 8 could be over here like this. However, there is a hidden second option for the arrangement of the sides in these triangles. Well, if I have this 10 over here, I still have that x over here with a 45-degree angle. It's entirely possible that rather than have the 8 swing out there to create that side length x, that 8 could also have swung in to be something like this. And this arrangement of sides also works. You may recall that this was an example of the angle side theorem that does not exist, right? There are 2 possible combinations of side lengths and angle measures that we have here in the configuration of our triangle, and we can't say for sure which one is which. But we do know that this guy x over here would probably correspond to the bigger of the answers that we got, whereas this x with that possible configuration would correspond to the smaller of the 2 answers. Very nice. You now know how to use the law of cosines. You'll get a little bit more practice with it for homework tonight, and we'll see each other the next time that we see each other for a little bit of a rehash in class together. But until then, take care, be well, do something nice for yourself, and I'll see you when I see you. Goodbye.